第一组的话是把 land model 跟 atmosphere model 都 CO2 都增加到1140 ppm， 就是说在这一个 model 底下，它同时在 land model 会感受到 CO2 增加让 transpiration 就是变小的效应，同时也会感受到就是大气里面因为 CO2 增加 radiation imbalance 造成可能降水的改变。所以在这一组的 sensitivity test 里面，就是两个效应都会共同去经历到，造成它的 runoff 去改变。那他还做了其他两组 sensitivity test， 第一组是在大气模式增加了 CO2， 但是 land model 不增加，所以对于 land model 而言，它还是在一个跟过去往常一样，是 CO2 是一样的，所以它只有经历到就是大气 imbalance， 然后造成降水改变。那另外一组就是只去改变 land model 的 CO2， 然后大气的 CO2 还是不改变，所以在这个状况下，就是你的 land model 是有感受到 CO2 增加，所以它的 transpiration 会改变，但是进来的降水大部分时候是不改变，但是他有提到说可能会有一点改变，因为现在这个 model 是 carbon model， 所以现在 land model 因为 ET 的改变，所以其实也有可能会不小心去影响到进来的降水。对，所以就这边是会因为 carbon model， 所以会造成讨论上可能会有一些大气跟陆地的交互作用。对，那所以这边就主要是想要去拿3组不同的 sensitivity test 来去看说，到底哪些地方是由 radiation 去主导为主，还是由就是 biophysics 去主导的。那在这边 carbon model 跑出来的空间解析度是1度，那但是因为它后面要去做一些比较细致，就是像 river basin 尺度去讨论，所以它还用一个 carbon model 去把它降到0.5度去做分析。对。那最一开始的部分就是他想要先去看说，那 CO2 增加，就是不管在大气或是在陆地 CO2 都增加，那哪些地方的runoff 或是 flooding 是增加的？那他在这边做法呢，是先针对每一个地方去看说，它如果 return period 是100年的时候，那当时的 flooding 的 frequency 或是量是多少？也就是举例子来说，假设今天在台湾好了，就是台湾你的 return period 是，如果要100年，它对应到的 flood 是100好了。那如果我们今天在动了 CO2 跟动了 CO2 的情形下，那如果今天它的 return period 要达到100，只需要50年，那就意味着说它的 flooding 的 frequency 是变大。那也就是说，如果今天 return period 变小的话，就相对 control 是小100年的话，那它就是 flooding 会增加。那反过来说，如果今天它的 return period 是大于100年，就是代表说它相对于 control 它的 flooding 是变少的。那所以对应到这张图，就是在这个 CO2 在大气或陆地都增加的情形下，如果它的 return period 是大于100年，就代表说它是相对于 control flooding 变少的。那这些地方大部分就是在一些中高纬度或者是一些像南美洲的岸边的这些地方。那反过来说，如果在 return period 是小于100年的这些地方，就代表说 CO2 增加的情境其实是让它的free flow 是变大。那这些地方就是这些蓝色的区域，就是一些东南亚或是非洲或是南美洲、欧洲的一些地方。对，那所以在第一步呢，他就是看到说，就是在这些地方它的 stream flow 是增加。那下一步他就想要看出，那这些增加的地方到底是由植物的效应贡献而来的，还是由就是大气的 radiation 改变造成的？所以他就进一步再去看说，就是我今天只去动 land model 的 CO2， 也就是左边 C 这张图，跟右边这张图 D 是只动大气的 CO2， 去看说。各自只动了某一个 model component 的 CO2， 那它的 return period 会怎么去改变？那举个例子来说，那像非洲这一块地区好了，那在就是 biophysics 这边，其实它的 color bar 是红色的，就意味着说植物的这个生理作用其实是会让它的 return period 是变大的，所以也就是它的 stream flow 会变小。但是在 radiation 这个地方，它这边就会变蓝色 color bar， 就代表说其实 radiation 的效应反而是让它的stream flow 是变大的。所以其实在这个地方就是主要是由 radiation 的贡献造成这个地方其实是会 stream flow 变大。 那所以其实就是可以把 global 里面就是 stream flow 变大的地方拆成3个 category。第一个就是主要是由 radiation 这个贡献去造成，就是只动大气的 CO2 就可以看到它有很明显的stream flow 增加，就是底下这张图的橘色区域。那第二个就是只去动 land model 的 CO2， 然后就可以看到很显著的，就是它的stream flow 改变，就是绿色的区域。然后以及就是我2个效应其实都对这个 stream flow 增加都有很明显的贡献，就是蓝色的区域。那它有去各自去分析这一些地方它的为什么会 stream flow 增加。那先从橘色 radiation 的这个地方为主好。那它有分析一些变数，然后就发现说，其实在这些橘色的区域的话，其实它的降水在 radiation 这个 run 里面都有显著的增加，就是这个它是最主要的 driver， 让它的 stream flow 变大。那就是因为它的降水增加，造成它的 soil moisture 变大，也就随之让它的 stream flow 变大。然后他有提到说，就是因为在 CO2 增加的状况下，其实这个地方有一些暖化的效应，其实也有可能是让这个地方就是降水变大的主因。然后另外一个就是绿色的部分，就是由 biophasic 效应主导的。那这些地方就他有发现说，它的 transpiration 都有显著的变小，那其实就会让它的 soil moisture 变大，进而造成它的stream flow 也会变大。但他也有发现说，在这些地方，其实它的降水也有稍微的增加。那他说这可能是因为 carbon model 会有一些 indirect 的效应，就是因为现在 land model 2比较少的 ET 到大气里面，可能有一些就是交互作用，让这些地方的降水随之增加。但就他这边就没有细讲说是为什么会有这些机制。对，然后最后一个部分则是就是蓝色的区域，就是在东南亚，然后美国的东南部跟澳洲的东部这边，那这些地方就是他有分析，然后就发现说，就是的确这些地方是有感受到因为 CO2 增加，所以 transpiration 变少的效应。那其实他在 radiation 减 control run 的这个实验里面有看到说，就是因为 radiation 这个效应造成它的降水增加，同时也让它的 soil moisture 变大。所以在这些地方，就是它不只是 CO2 的效应去主导，同时也有一些 radiation 的效应去主导，才造成它的stream flow 是变大。所以在这边就是他算是回答他的第一个科学问题，就是想要去了解说，就是哪一些地方是由植物跟或是 radiation 主导。那主要这些植物主导的地方就会是这些绿色的区域为主。
然后再来，它就是去分，就是就是比较强的 stream flow 跟比较弱的 stream flow。然后他用95%跟5%代表 QP 跟 QO。那这个 QP 就是应该是比较湿的stream flow 比较强的季节，它是主要是用季节角度去看。那他就先去跟过去前人的研究去做一些验证。那上面这张图就是它去验证这个 1118run出来的结果。那主要是百分比的部分是就是它跟过去前研究resale 一致的面积百分比，那就是可以看到说79.2、80.2跟68左右的面积是与前人的研究相左。那当然这是定性上的一些差异。那定量上，当然因为它不可能完全一样，所以在尤其赤道部分会有一些定量上的差异这样子。那再来就是说，他去讨论说，就是 Q-mean、Q-low 跟 Q-peak，在不同纬度下的贡献是什么？不同区域下的贡献是怎么样？那可以看到说，这个 Q-low 主要是在高纬度的部分是增加。那 Q-peak 主要是在这个赤道部分增加的情况。那总体而言，就是stream flow 都是有增强的这个效果，在这个fully coupled 的情况下。那再来就是他为了去讨论说，就是因为这是空间的分布情形，那他就是去做一个中浓密，主要是要去看说到底是fully coupled 主要是有把 physical 还是 radiation 去trigger 这个 stream flow。那比较深的颜色是这个 fully coupled， 那比较浅有依次是这个 依次颜色申请分别是这个 biophysical 跟 radiation 的贡献这样子。那可以看到说，在比较尤其这个 Q-Low 就是stream flow 比较弱的时候，主要是还是大部分纬度区都是主要是由这个biophysical 所去贡献。那因为植物的那个气孔关闭，那比较少的蒸发散贡献到 release 到大气，所以比较多的水分留在这个地表之中，所以 stream flow 在大多数纬度都是增加。那如果是由 radiation 去trigger这个 stream flow 的话，那因为就是更多的show wave 进来，那大气温暖化的一个效应，那更多的蒸发散，所以这个更多的水汽 release 到大气中。所以整体来说，就是如果以 radiation 的角度去看的话，去 trigger 这个 stream flow 的话，留在这个地表的水会比较少，所以这个 stream flow 整体来说会比较偏弱。那这样的情况可以反映在这个 soil moisture 的分布上面。那可以看到就是 radiation 特别是在高纬度的地区，就是都是 soil moisture 都是增加。因为高纬度地区主要是，如果冰雪，就是急剧它有一个 amper 法公里的一个效果，就是如果雪融化，更多的水就会就是往下渗入到地表之中，那更强的这个 run off，stream flow 就会反映在这个高纬度地区，所以这边其他纬度都主要是由这个biophysical 贡献，那比较高纬度的区域就主要是由这个radiation 去 contribution。那除了地表过程之外，就是它似乎有一个正的 feedback， 就是降雨增强，然后更多的水就是落到地表，然后造成这个 stream flow 增强。那在高纬度地区的大多数的部分就是水，它似乎是一个water cycle 在这里似乎是一个增强的一个状况，就是循环会变快这样子。虽然他没有提到，但是这是我就是看了他这些图的一些想法。那除了探讨说就是这种全球的 global 的 distribution 之外，那他想针对就是不同的 river basin 讨论，所以他就是在这边又针对不同各大洲的这个basin 去做这个就是跟 control run， 就是当你动了这个biophysical 或者是 radiation， 那相对于 control run 它的stream flow 是增加的是减少。那可以看到在大多数区域都是增加的一个情况。那从这个命的部分，我觉得不用特别看，就是看 Q-Low 跟 Q-Peak 的部分。那 Q-Low 可以主要看到就是都是在赤道地区它有一个stream flow 都有增强的一个情况。那下面这张它绿色代表说是biophysical 的 trigger 的 stream flow 的一些效应。那蓝色部分的是 radiation 去 trigger stream flow 的一个效应。那如果是蓝色加绿色，就等于就是这个黑点。那黑点如果跟这个浮力发动去一起去 trigger 的效应的话，如果有重合的话，就代表存在一个线性的关系。那如果就是距离这两个点如果距离差远的话，就是其实这不同的 river 之中有存在一些非线性的一些 effect 这样子。那可以看到就是在赤道地区的这些 river， 主要还是都是由这个 biophysical 所去 trigger 的让 stream flow 增强的一个效果。那我后来去看就是这几个蓝色比较占比例比较大的部分，就是主要都是集中在高纬度。那跟前面这张图比较一致，高纬度主要是由这个 radiation 去贡献。那就是进到就是最后 discussion 部分。其实它这篇文章主要就是要告诉我们，就是biophysical 的效应对于这个模式来说是很重要的。我们一般就是谈到这个极端的事件，就是极端的洪水可能是由极端的降水区去造成。 但是很少会去讨论说，就是植物这个效应在模式中扮演的角色。那它这边主要是要去highlight说，在不同区域，就是不同纬度，植物或者是 radiation， 它去对 stream flow 的贡献。那在低纬度地区的话，主要是有这个biophysical 的效应。那在北半球高纬度的部分，主要是由这个radiation 所去贡献这样子。那我报告到大致到这，我希望后面就是大家讨论。
好，先谢谢啊。所以，首先呢，我是觉得这个它的实验设计还蛮有意思的，因为大概之前比较少人透过这样的实验设计来想 CO2 下对全球气候的影响或水文的影响。那因为之前不管是你说我们看到 IPCC report， 那这些 CMIP 从以前 CMIP 3、4、5、6的这些实验，那就是CP 这些 scenario 下，就是好，我 double CO2 或 CO2 浓度随着某个东西一直加上去，来看未来的降水会怎么样，或未来的淹水倾势会怎么样。那时候做大概都是所谓的负荷的这个的概念，就是因为就理论上就是整个大气二氧化碳变多，那就是都变多嘛。不会说只有大气变多，陆地不变多，比较没有这回事。毕竟还是从陆地 release 出去，所以都在想的是这个负荷的 case。那慢慢的大家在探讨，特别是可能比较陆地模式的这群人，觉得特别弄生态这些人，觉得因为 CO2 浓度的上升会影响到 transpiration， 就是我们过去这1、2个月在跟同学们提。好了，所以他们就设计了这个实验，我就觉得还蛮有意思。就是好，那我们如果把它拆开看说，如果只有大气增加了，那 radiation 那部分在陆地没有感受的，那就是第3个实验。就大气温度还是升温哦，因为1000多 ppm， 所以大气还是升温，进来的 long wave radiation 或因为降水的改变都还是会变，所以等于大气的 forcing 有变，但陆地上的植物感受到的还是很低的二氧化碳，大概是这个样的实验设计。所以是蛮有意思的，就是好，我先不要看 transpiration 因为 CO2 的变化，但是温度的变化有没有在陆地上？是有的，因为二氧化碳已经变高，所以进来的 radiation 会变多 ，long wave radiation 变多，然后加上降水的改变，所以这个部分是有的，就是陆地还是感受到温度的上升，那大概就是这个事。那大概你们在介绍的时候有提到，理论上大气的 forcing 可能不会变，在如果只有 physics 的这个情况下。那如果 physics 的这个，也就是只有陆地二氧化碳浓度变高，那实际上它只是说让植物的行光合作用的效率可能变得更有效率，所以 transpiration 减少，可能影响到 soil moisture， 那影响到 soil 的 evaporation，overall 影响到蒸发散量到大气，那当然也会影响到近地表的温度等等等，会有一个差异性。那大家可以从它的 physics 跟 control 来看。那有没有再多去看说这个跟这个它的降水的变化？刚才好像是想讲，应该只会有一点点的影响。那到底它背后的影响，例如降水的变化是多少？有在看这个？
就是他是在讨论这张图，就是特别把绿色圈的地方，就是他有去看，就是降水、收摩圈那一些。或是 transpiration 这些变数的变化量，然后但他是有看到降水有改变，但好像是不显著。然后他就说，就是这件事情，就是可能是因为 carbon model 的 indirect effect 造成，但可能不会是一个主要的机制去影响。
就如果说 transpiration 的改变的减少，并不会让降水有那么大的变化。对。
但它也没有直接去看降水，因为这个已经是 end product，
对，
这是 comma from 的结果。
因为这边是 reference
好所以一样在高纬度地区有一些变多，
对，稍微就是如果是单纯讨论半径的效果，那如果是 radiation 的话，好像就比较明显，就是高纬度地区的降水会增加比较多。
你看中间这张图是 phases 那一组 sensitivity test， 然后右边这张图是 radiation
的 difference，
对，
所以就减掉减掉 comma flow， 对，然后只有在 low， 因为现在又是看 low 跟 peak，
这张图没有 low 跟 peak，
它是好像是负，
这是平均。
最左边这张图是负减掉 control， 然后中间这张图是负减掉 phase， 然后右边就是负减掉好 Q 命 low peak 没有关系。
所以降水是有了一些变多，都红色的。
对。
不知道为什么，就降水在这两个跟 control 比起来都变多，这个好像出乎意料的蛮 consistent， 都是红的。好，那当然 soil moisture 你会看到有正有负，那跟蒸发的变化可能又有关系。上面找有正有负，但在降水这部分好像都是正。好，所以同学们对于这个实验设计，我是觉得蛮有意思的，不知道大家同学们有没有体会到，就是原来就是这个整个 CSM， 因为他们跑的也是 CSM， 所以 CSM 其实也可以这样来看这件事情，就是把 file 的这件事情独立出来看。那如果说要跟你们之前练的论文来互相比较的话，那是要用哪一个比较合适？
其实大部分应该都不能直接比较，因为毕竟这边是卡口，所以其实大气有点被改变。但如果硬要说跟之前 paper 比较像，应该就是最有比这就是因为我们在 offline 主要改的是 land model 是有当面改 force，
对，所以应该是那个assume 这个对于大气 force 的影响 minimum，
对，但就如果我们要 reproduce 这个的话，就变成这种大气为了 forcing 要丢一个暖化情境下的大气 force， 对，固定
要改。不过如果只看 CTL 跟 physics 这一个，因为你刚才也讲了，降水的变化相对少。那当然，蒸发一定有它的影响，因为蒸发应该都显著的减少，是吧？
主要是检查而已。
对，
因为我昨天有跟他讨论到问题，就是当你植物，就是植物变大，那你系统会关闭。那植物变大的话，你降水如果落在植物的表面，那到底算不算？对，就是它如果没有流到下面，到底这个会不会对径流会产生一些反思？因为它文章里面没有特别讨论到这个问题，就是你植物面积变大，然后雨落在叶面上的这个问题。
那这个就是在另外一个叫做 canopy evaporation 上应该可以显示出来。不过这要回过头来看它是否它的植物真的变大，要看它的用的 component setting。
它 MAI 是会随着 CO2 改变增加
变大，那就会，那 canopy 的 intersect 就会变大。
因为它 supplementary 还有放这3个component 的改变，对，然后但它其实就主要还是在描述 transpiration 的 component， 尤其是在这个
OK
test。
那有没有提到说减少的百分比呢？
应该有，但我没有细看一下，
没关系。好，有这边你有提到 leaf area increases with high CO2 but no dynamic exchange。那这边 同学们，这边就在这个在 model 里面的一些更 detail 的，或者比较技术性的说法，就是 leaf area 会增加，那也就是这个叶子的面积会因为在高浓度 CO2 下它会变大 ，fine， 就合理的状态。但是它的 dynamical vegetation 意思就是你树会不会变草？树会不会被雷打掉之后怎样？这些 model 他们也有在模拟，这就叫 dynamical 的 vegetation， 就是不同的 vegetation type 之间的转换，那没有被描述在目前他用的这一个版本里面，但是叶子是会长大的，大概是这样子。好，然后你可以回到一个结论，就是在干季的时候，我想这是一个有意思的东西啦，就是 for low flow， 是否要在 low flow， 就是这个所谓的 physiology effect 才会出现，好像结果是这样子。
我觉得他这边好像主要是要强调说，在这个 Q low 的这个情况下，
那 Q low 是
就是属于 low 的弱，
比较弱，那或许是干季，
对，算可能，因为它没有特别主温跟 drop，
OK，
那一般我们的理解就是说啊，它比较干，好，增加比较多，特别是在这些 river basin 地方，说在比较弱的时候增加比较多，但是在比较强的时候增加可能多，反倒是只有在高纬度的地方，但是在赤道地区主要是有大 physical 贡献，而且在 Q low 的时候。
对，那这个就回到，就是 Q mean 的时候可能看不到，是吗 ？Q mean 的时候可能看不到 biophysical，
最上面这3张都是负的结果，然后最下面一张才是把负的结果拆成就是植物跟radiation的贡献，然后就是命的话，其实在热带地区其实也是有些改变，那就是没有特别是谁贡献为主，对，然后但就是弱的话就是主要都是热带改变比较多，对，但是就是有一些地方其实它的就植物的效应其实是真的蛮强的，对，然后如果是比弱的话，就是主要的影响的位置都是在一些高纬度的地区，然后那些地方又是以 radiation 风险，这样子是大概是情况。
所以似乎有可以拆开的出来说，radiative effect 在高纬度的重要性，那以及 biophysical 的 effect 好像在 low 的时候会出现，但好像又比较偏向在低纬度。那也是那边的，因为这个就会跟是否有森林绑在一起。如果他要讲 local， 我觉得现在这边会有2个层面，一个是 local， 因为你改变了它的 physical 的这个 experiment， 在例如撒拉沙漠，理论上它的应该那些不会被影响，因为你压根那边就没有。但是这个又是一个 fully coupled model， 它可以看到有 remote effect， 所以 Amazon 感受到的这些 ET 改变可能会影响到其他没有树的地方。我不知道它背后有没有探讨这个 local versus remote 的 effect。
这边比较少，对，就单纯是看那个效应发生，然后那个效应发生的时候，那个地方个别的抓有没有改变？但当然里面可能会有一些 tailor， 对，说不定，但是目前在这一边是没有特别没有讲，
因为这个我觉得因为它2个尺度不一样，一个是你 radiative effect 是 CO2， 那基本上是全球都感受到这个改变，但是 physical 那边只改变 transpiration， 那当然那些 grass 就是只要有 vegetation 的一定就会被影响，蒸发就会减少，但是绝对不会在沙漠里或比例上的问题，在 Amazon 一定感受到最多的改变，但是实际上它变化不一定要最大。就是从这里，不管是 mean 或 low 或 peak， Amazon 的变化其实相对 小很多。哦，所以这是一个有意思的点啊。或许它那个地方是一个改变量很大的，就如果有一个17的改变的话，可能那边减少最多，是吧？有没有17的变化或 transpiration 的变化？
哦，我们这边有画，
有，
但它有放在什么上面？
那个图长相是 local 17的变化最多，就是应该是有数的地方17变化比较多。
对，我记得至少有
是，但可能就是 Amazon 或刚果变化比较多，但它的效应上是两回事了。
也就 Q 的空间不一样。
对对对，所以我觉得这边是另外一个有趣的点，我觉得同学们可以想一想，就是在 free couple 里面，你改变的东西其实跟后面他探讨的东西，空间上不一定是同一件事情。那当然，这是我们知道有 Taylor connection 所导致。你看。好，同学们，对这边还有想要拿出来聊的东西吗？就是觉得还蛮有趣的 paper， 那有没有？或任何我看不懂，对，在 discussion 这里，有没有觉得？因为你们现在在跑的模式就是 CLM， 那你们也做过了 physiological 的 effect， 就是将 CO2 浓度变高。你也做了 radiative 会造成的 effect， 就是降水的变化或 radiation 的变化。那因为我们现在呢会是一区一区的，因为我们5个组大家就 focus 在一个区域。其实你们应该已经可以感觉得到，就是我们在做 group presentation 的时候，就是同样的变化，不同的 region 变化是不一样。我想这个大家要，我想这个概念蛮重要的。同样的 forcing， 不同的地方变化会不一样。我想你们可能，因为当然现在你看你自己的 basic 大概感觉不出来，但是我们一起在 present 的时候，就是例如像在澳洲的反应，好像跟我们在 Amazon 的反应不太一样，虽然都是同样的 forcing， 对，我想这个是蛮有意思的一个东西。好，那这边我想就是它着重在 low flow 的 physiological effect 好像比较凸显出来。那这个是我们之前好像比较没有看到，或没有特别去看说，当 CO2 浓度变高的时候，我们着重在比较干季是不是反应会比较大，或流量比较低的时候反应会不会比较大？我们好像没有这样才去看。或许这是你们到时候再继续看下去一个可以抓的点，就是跟植物它绑在一起。那因为在湿季的时候，应该就被这些降水的 pattern 所 dominate。那在干季的时候，可能跟蒸发比较有关系。那干季的时候的蒸发，所以这时候 CO2 浓度上升，它的效应就起来。我想这是在这边为什么 low flow 会特别容易清楚的部分。我补充到这里，你们还有没有要加码？
都是增加，那干季也都增加，然后就是这样可以这样讲。
都是增加。你说在没有，现在是对 flow 而已。
对对对。但是比较密度
这个东西倒是前2篇论文书没有提到。前2篇论文有在看干湿季吗？有没有前2篇的 lead 的同学们？前2篇论文有在看干湿季，就是过去的 trend， 因为他们都在讲 CO2 对降水、河川降水的 trend。那有在分干季、湿季来看？没有，
那边好像没有，
好像没有。所以这里就看得更细了。我觉得从它的 abstract 其实有读到，就变得更细了。
我那边是 global， 对，就它大部分的分析是 global， 所以
对，但我觉得还是可以看，
应该对会有 seasonal，
对，应该可以看 seasonal， 而且就我觉得从这里我学到，就干季要更明显，应该要。那我的意思，这个是你们往后再分析未来这2个月差不多 他2个月我们撑到2个未来的这些日子里，可以多分析的，可以着重在它不同的 seasonality 的部分，好像你就会让你的效应好像看起来更大这样。好，有没有 comma 那个 model 的一个结果？任何一张图 ，comma 就是刚才那个 model comma CMA， 就随便一张图，没有，这个算吗？算了，因为你用，但这个等于用 comma flood 的 model 再去算它的 return period。对，那 comma flood 那在回去上面，就是刚好，这是一个日本 model， 是。
我没有自己看，我也是他只是讲他有一个 model， 然后做什么事情。
好，那等一下雅杜下一个 presenter， 其实他的研究用到了这个 comma flood 的 model。那概念上，其实你们现在有知道了，其实这个 comma 就有点像是我们在讲我在介绍 COM 的时候那个 RTM River Transport Model， 所以把CSM 应该说 COM 它的 runoff 的 output 抓出来去 drive comma flood model， 所以它等于是一个另外一个 offline model， 先跑完 CSM 再抓出来去做这个。那这个 comma flood 的一个你把它叫做水文淹水潜势的模拟哈，它是 for hydrodynamic downscale river discharge， 所以它其实可以模拟出淹水的倾势，你只要给它滴一验就可以。那这个晚一点。就等一下，雅杜也会刚好讲到这个东西。那只是他用的可能更高的 resolution 下来看，可能是个淡水河，假设是这样的一个空间尺度上。那这是日本他们东京大学发展出来的一套模拟，大概这样子，可以吗？好，那我们再谢谢景彤跟许杰。好，那我们休息一个5分钟，等一下回来就进行我们下一个演讲。好 ，Hello。All right. Good afternoon. It's my honor to have Professor Yadu Togoro here to give us a seminar. And his talk here you can see is representing anthropogenic water and nutrients flow processes in Earth system models. Let me quickly introduce Yadu. So right now, Yadu is an associate professor at Michigan State University at the Department of Civil and Environmental Engineering. So why Yadu is here? So he actually right now he's a Fulbright scholar in Taiwan. So it's a Fulbright 学术基金会, and it's kind of from the U.S. they initiate this kind of scholarship program, and the researchers or professors at the U.S. universities they can apply globally basically. And then since Yadu and I had some collaborations before, and then he decided to apply the Fulbright in Taiwan. And then in that project, because we need to write a proposal, so we kind of write, Yadu kind of try to incorporate some river flow simulations in that proposal. So we are still working on that part, and maybe Professor Huang can help us in the next couple of months. Yadu was here since August till now, and because it's a half-year program, so he will stay till next January. So later, if you want to talk to him, that you can contact him or do me as well. All right. Okay. So with that, then let us welcome Yadu Togoro again.
Thank you, David, for the nice introduction. It's a pleasure to be here. First of all, it's so nice to be in Taiwan, my first time, even though I lived in Japan for 5.5 years, not far away from here, and I traveled to many countries in Southeast Asia, actually, whatever, Thailand, South Korea, Vietnam, Laos, and so on. So many countries, but I somehow missed some opportunities I had to come here for technical reasons, and finally I'm excited to be here. And also it's a pleasure to be able to talk about some of our work in this class, this opportunity. Thank you, Lily, for that, and also for the introduction. I will start with my lecture, and the title, as I said, it's I will talk about anthropogenic water and nutrient flow processes, meaning that in large-scale models, hydrological, climate, and these days we call them Earth system models when they are coupled. So how are anthropogenic water processes like irrigation, dams, and groundwater pumping, and also nutrient. When we do irrigation and crops, there's going to be a lot of nutrient coming out of cropland. So how are those simulated in this model is the topic here. And let me start with a little bit of background. When we talk about these Earth system models, my focus will be on the land component, the land surface model. And people here are using CLM, right? Or
some may use CLM, and I think Professor Huang used TAM model as well.
Okay, TAM model. Okay, So I'll talk about CLM a little later, but basically what I do is with models like CLM, land surface model. And I wanted to start with this one. This is a kind of diagram from 2003. So this is where all of this modeling started a long time ago. In 1960s, when Shuki Manabe from Tokyo University went to Princeton and started developing these models. So basically, bucket model, right? Simply there is a bucket that represents the land surface in the climate model. And on the bucket, there is some rain, no vegetation. I'm talking about 1960s, by the way. And no vegetation, just some rain, some capacity of the bucket, globally applied uniformly for every place. And when there is excess rainfall, in this representation, you will see some subsurface, but there was no subsurface even in the beginning. So some rain comes, and when the bucket overflows, there will be runoff and so on. So it started with that, and I don't know if any of you have seen or read this paper, particularly this one by Fisher and COVID 2020. So they saw how land surface models evolve over time, and I put this still bucket model on the left side here. Very simple representation. Canopy is implicit. There's no explicit canopy. And then this evolved. You see this surface energy fluxes and storm resistance and stuff coming in the 80s because the plant physiological communities and hydrological climate modeling communities realized that plants are important drivers of land and atmosphere exchanges, right? So they started putting those, and then gradually more stuff here, big reservoir wetlands and so on. But even until now, this is 10s and 20s, until only very recently people started talking about these anthropogenic processes, human processes. A lot of advances, and here you see this is a climate model, and this is called Earth system model now, where there are a water cycle, carbon cycle, nutrient cycle, all coupled. So we went from simple models to a very sophisticated model, and today if you look at the representation of land surface models like CLM, then this would be a kind of representation. You have a lot of these surface really fluxes, latent heat, sensible heat, snow portion without snow, and same thing on the ground, energy balance solved at a portion of land with and without snow. They're pretty sophisticated models like this one, right? But my point here is, yes, that has all happened, but there has been very, relatively low emphasis on the human components. Even though around the year 2000, people started talking about this term Anthropocene. I think many of you know about it, right? Anthropocene. Yeah, Paul Crutzen published a paper in 2002, Geology of Mankind or something, and in that paper they coined this term Anthropocene, saying that we have passed the 10,000 years of stable Holocene period in geological age, and now we are in Anthropocene where humans are, even stronger drivers of climate or the Earth system compared to the natural drivers. So they started talking about this, but in these models at that time, early 2000, not this, even in 2010 when I started my career, my PhD around 2008. Not much done in this area. And the issue is, I just saw here very simple stuff. Population growing and then water demand is growing and humans go and exploit the land, deforestation changing to croplands, and when you have croplands, we need irrigation because there's not enough water, we take water, and then to do irrigation you need to go and build dams and completely modify the landscape and so on. So without doing that, representing that kind of human modification of the land surface, how can you simulate today's water cycle? And I think a lot of people say that also. Sometimes I like calling modern day water cycle, not what we used to have in the beginning of 20th century. Mostly pristine. So how can we simulate the water cycle with these models by completely ignoring the human components, right? That is the big question we started asking when I started my PhD in 2008. And the other part of the story is there's increasing demand, but this one it shows there's a small image here, but whatever you see red color on this side, this is decline in water availability. Let's not go into the details over there. This is figure from my recent paper published in Nature Climate Change. Whatever you see red, you see in a lot of places, water availability will decline, but there will be more demand. So we're going to go and change the water systems more because we need to fulfill higher demand from smaller water or lesser water availability, right? So this is where this comes from, and now let's get to the point about what these human forces are, or what are the key drivers when we talk from large-scale perspective. This can be debated. People working on smaller scale in some places, in urbanization, heat island, that can be one human activity that impacts that location. But from large-scale perspective, what are the key drivers of change in water cycle? So the first one is irrigation. So I think it's going to be a little not too strong. So irrigation on the top, you see irrigation, a map of irrigated areas, and the red color shows higher percentage, up to 80% or even 100% of the area irrigated, and in North India, East China, and Central and Western US, and so on. And then here, the bars show cropland increase, but if you look at the blue line, 1900 to 2000, irrigation rapidly increased. Recently, it started stabilizing a bit, but a lot of increase in irrigated areas. And what we did is, to fulfill those demands, we pumped groundwater. Because where does irrigation happen? In relatively dry places, right? In some places, of course, in Southeast Asia, there's a lot of rice planting, and people may do some irrigation there. But otherwise, wherever you see red, the India, North China Plain, Central, Western US, and so on, relatively dry, semi-arid places, then those are very fertile in terms of growing crops, but there's no surface water. So they just go and pump groundwater. And this map shows, again, it aligns, the red stuff here aligns with the irrigated areas right here around India. You see, pretty red groundwater withdrawal. This is groundwater withdrawal. And if you look at this line, it shows how groundwater use increased from 1900 to 2000s, rapidly going up. And this is until 2000 only, and it is still going up. So all of these have been, accelerating. And right here, again, the same thing, but I wanted to show some examples. The map here is the same as in the previous slide. So what is happening in the central U.S.? Maybe some of you may get interested at some point. So this is called Ogallala Aquifer, very highly productive agricultural system, which is called the basket of grains of the U.S. A lot of wheat and other grains are produced in that region, and they are consumed not only, they go to the breakfast table for all the, U.S. people, most of the U.S. people, not only that, but also they export a lot of wheat globally. So how is that produced? By pumping very deep groundwater. That has been recharged maybe 10,000 years ago. We are just pumping. We call fossil water because it's there like fossil fuel for a very long time, century scale sometimes. And they're pumping, and if you look at this is small, but it's depletion. The red color is depletion, reduction in groundwater table. That is up to probably 60, 70 meters or more in some places, okay? And same thing, I don't want to spend time, this is North China Plain, and again, this is Northwest India. This is primarily driven by irrigation, huge amount of water being pumped. And we recently visited water agency in Taiwan, and Not at this large scale, but still it seems there are some places where irrigation is happening and there are emerging groundwater depletion issues and so on. But this is what is happening globally, okay? And the other part that I put here is, and I already mentioned, to do irrigation, in some places they pump groundwater, in other places they build dams and divert water, right? So many dams were built during the 20th century. And if you look at this global map, at least on this map, there are dams everywhere in many continents. And when that happens, one thing is diversion and so on, but the other thing is, this is the case of Colorado River, where the flow used to be like this in the pristine or natural conditions. This is good, and then in the 1930s and 40s, U.S. started building huge mega dams across the Colorado River. What happened is the flow, now, they divert water somewhere, they send it to California, they irrigate crops, and that water evaporates and goes somewhere. Basically, today there's nothing going down to the ocean in Colorado, okay? And then, if you look at the, river flow, let me go to the modeling issue here. If you simulate the Colorado River flow by using any river routing model, it seems you had a discussion about river hydrodynamic model, and CLM has a river routing model. If you do Colorado simulation, you can still get this green line if you don't have dams represented. Very nice natural rhythm there. During wet season, the flow goes up and comes down, right? But the actual flow is like this because the black line, heavily regulated. And the point here for us was, can we simulate that black line? In this case, it looks pretty simple. Maybe, I don't know if you're imagining, more or less a straight line, so just, constant release of water, right? But in many cases, it's complicated. You need to know how water is released exactly. So we did this, I'll talk about this later also, and then when we started putting dams, we get this red line over here. So instead of having this green line from the model, we get the red line. So we are better simulating the river flow over there. And this is another case of building dams. Maybe some of you have heard about it. LOC disaster in Central Asia. It's called one of the most disastrous consequences of water management during the 20th century. This is very large scale. And right here, I even put the numbers. 1,100 cubic kilometer is enormous amount of water. In the US, the largest dam is called the Hoover Dam. It impounds water. That has a capacity of 35. So this is 35 times maybe 30 different 30 reservoirs. 30 times of the largest US reservoir. That was of water here. That's why it's called LOC, not reservoir or lake. That completely disappeared in 40 years because of these human activities, because they simply diverted water to irrigate crops and so on, right? So these kinds of things are happening, but again, going back, models do not really represent these human activities. So let me move on to what we did, unless anybody has a question or anything. This is just background information about why this is important. Maybe some of the stuff you already had heard about, but some maybe not. Okay, then let me move on to this one. So this is a typical representation of grid cell in the land surface model. As I said earlier, very sophisticated, biophysical and biogeochemical processes here. And then there's some soil or groundwater process here. And there's river runoff generated, and that is routed by using some kinds of river routing models, right? That is the typical representation. And this is something that the cartoon is something I developed for Japanese. CLM is pretty much the same. And as I already said, the issue was there's no representation of all the human activities that are changing the landscapes, water cycle over large domains, right? So what I did in the very beginning, this study was published in 2012, was putting, if I go back here, nothing there, just vegetation and natural processes and river flow. We added a bunch of things like crop growth and then water withdrawal, reservoir, environmental flow, and then subsequently we added also deep groundwater, taking the soil layer up to 100-meter depth. So with this framework now we can simulate the integrated water cycle. Integrated can be defined in many different ways, but here I'm saying integrated in a way, in a sense that the natural water cycle is integrated with the human component. There's crop growth that simulates crop yield and then irrigation demand. And then we go and get irrigation demand from river or sometimes groundwater if that is the case, and also try to lead some environmental flow. And then there's industrial domestic demand and so on. So this is what we developed. And in the next couple of slides, I will show some results quickly because I will have some more detailed stuff from CLM later on. So what we could do with that is we take these irrigation areas here and we simulated irrigation demands. It's pretty small. Let's not spend too much time on this one because I have something similar later on. So the model now can simulate the irrigation demands globally, okay? And we validated this. How do we know the model is doing well? This is country scale validation of irrigation demand. On this side, simulated. This is observed. So the model does reasonably good job. We are doing it at the global scale, putting some limited data like irrigated areas and some other parameters, and we were able to simulate that. And then we also simulated the irrigation-induced surface temperature change. Because when irrigation happens, one thing is it alters the water cycle, but as you guys know, it also alters the surface energy balance, right? So there will be more evaporation, evapotranspiration, and that will cause alteration in the surface energy balance. If there's same amount of energy, then there has to be less sensible heat, and because there's going to be more latent heat, right? And that causes surface cooling because more energy is used for evapotranspiration. So we see this cooling nicely simulated, even though we cannot really tell whether this is accurate or not, but we see up to 4 degrees or more cooling, surface cooling because of irrigation in these heavily irrigated areas. And then that is the irrigation part of the story, and also we put all of these big reservoirs in the model at a global scale and simulated how the flow is altered by reservoirs. And again, I already showed this graph earlier. The green line is before having reservoirs, and then black line is the actual observation, red line is after having reservoirs. So we can see, the model tries to improve the stream flow simulations when we have reservoirs. And by the way, this is something that I did in 2008-10 in the Japanese model. Today, CLM still doesn't have this. CLM gives you the green line, that's it. And if you do Colorado stream flow, if you want to simulate Colorado, why I put, even though this is old, a decade old, why I wanted to still emphasize is people need to talk about it. Is there somebody who can simulate or who can implement the scheme in CLM and nicely reproduce something like this? So far, this doesn't exist. So that's why I'm still keeping my own slides in my presentation. If it was old, like the bucket model, we don't need to talk about how the vegetation is simulated because a lot of these models do the vegetation part in a very sophisticated way, photosynthesis, all kinds of things, right? But this part, it's not there. CLM is one example. There are other models globally, any model. And we are using the Orchidee model in our project from the French model. I think it's the same story. There are some irrigation schemes, but the reservoirs are not there. So yeah, that's the story. And then this is the Japanese model that I was working with until I'm still working with that. And then this has now been integrated into a Japanese model, climate model for Earth system model called MyRock. And now it is called MyRock Integ Land. And all of the schemes that I just talked about quickly sit there as water management, irrigation, dam, and so on. And this is the complete framework. So that is where we are in terms of the work that I was doing before. Okay, then let me move on to the second part of human activity representation in the model. And here I will talk a little more about CLM and more details about how things are represented, where we are today, and so on. And I wanted to make a transition here by saying, the work that I did at that time and all the outcomes that I showed today are at the global scale. We can show nice global maps, and sometimes some people are fascinated, we can do this at the global scale, very nice. We can show some hotspots of groundwater depletion in North China, Northwest India, or the United States, and so on, right? But there's also other side of the story. How are those results useful if we want to, improve water management? And also probably reflect real world water management practices. How is irrigation done in the real world? And we're talking about big grid cells here, just putting some limited data into the model. And also, the scientific community talking about super high resolution modeling at the global scale. And this terminology, again, hyper resolution, came around I think around year 2010 or something. Princeton University professor published a paper saying we need to do hyper resolution modeling, 1 kilometer globally, and produce something that is really good to understand or improve scientific understanding, but also at the same time locally relevant. If somebody says, "Can I use your model to do some water resource management or planning?" Yeah, in 1 kilometer, it's pretty good probably, right? So that's the discussion that came around 2010, almost 12 years ago, and a lot of people started working on that. And we are not really doing hyper-resolution 1 kilometer globally yet, but we started thinking about how about zooming in to some of these places and capture the actual changes happening and utilize more data from local to regional scale observations and so on. And one thing I did in the very beginning, this was done in 2014, before I go here, this is zoomed in version of groundwater depletion from a global model. So this can be simulated by CLM, I'll show you later. So you see big grid cells here, I think 50 kilometer by 50 kilometer global model. And if you look at here, this is somebody in California, they say, oh, in our area, there has been 450 millimeters of groundwater depletion every year, right? That is Central Valley, California. But, within 50 kilometer, there are all these small farms, rivers, ridges, valleys, and so on. So all of those are gone in these kinds of work. We can only show bird's eye view. So I started working at 2 kilometer at that time. This was never published and never used anywhere. But if we go to 2 kilometer, this Central Valley right here, see, this is the these are Sacramento and San Joaquin rivers over there, and you see very nice patterns of where groundwater is depleted, where the rivers are, and so on compared to this one, right? So this was kind of one of the motivations to do high resolution regional work in different locations, and that led us to also use of the community land model, CLM. There are various reasons about using this, even though I was using a Japanese model before, but let me not talk about it. This is a state-of-the-art model, very sophisticated model with each grid cell that can be divided into many different patches, like urban and then vegetation and crop irrigation versus irrigated versus non-irrigated, and so on. And you can change the resolution. We are doing at 3 to 5 kilometer right now, and if you are doing globally, you can do 1 degree, that is 100 kilometers. So there's a flexible framework, and you can assign different vegetation or land use types within the model. So we started using this, and the problem was again the same thing. As I already said, reservoirs are not there, but when we started using, there was a simple crop scheme and there was a very simple irrigation scheme, but even the irrigation scheme was simple. For example, it takes runoff rather than river flow, runoff from the grid, okay? And if there's not enough runoff, just local runoff. You can imagine in any grid cell there can be a lot of water coming from the upstream, but if you just look at the local runoff, it's very limited, and the model tries to withdraw that local runoff, and if there's not enough runoff, the runoff becomes negative. The model doesn't know where to get the water from. So we started working on this and substantially improved crop modeling and groundwater modeling and also nutrient modeling very recently. And in terms of the crop modeling, I didn't put too many details here. The crop model in CLM is based on a model called Agro-IBIS, developed at the University of Wisconsin-Madison for another model, and the developers at the National Center for Atmospheric Research, NCAR, where CLM is developed and maintained, brought that simple crop scheme and implemented it into CLM. So it can simulate, crop growth. You can specify planting date and let crop grow. You can put some fertilizer, water, and then you will have harvest. You will have some crop yield. That's what it does. But then we found that there are a lot of deficiencies again in this crop growth scheme in CLM. And a few of those is, by the way, I don't know if there's interest or many of you know how, what kinds of crop models exist. There are two types of models. One is like the CLM, large-scale hydrology, climate modeling communities developing crop models to, do a simple representation to not miss crops in these Earth system models of climate models. Far away, there is another community, agronomy community, field-scale people. They go to the plots and measure, infiltration processes, plant water use, and yield, and so on. And they develop, they parameterize crop models at that scale. And here I have this APSIM model. The APSIM model is on that side. Agronomy people develop this model for smaller scale applications. And then CLM has a large scale model that can be used at very big result, but only captures the, first order things about crop growth. So we combined these two in a work that was done in 2011 led by Bin Peng at the University of Illinois Northern-Champaign, and I was a part of that. And in this one, if you're interested, you could look at this paper, but what we are doing is crop phenology. This is CLM simple in plant, and there's leaf emergence and grain harvest, okay? We try to simulate these major crop growth stages. We miss a lot in between that. You cannot see here, but germination, emergence, and then flowering and grain filling, all kinds of stuff. And why those are important is there's always nutrient or water stress during that period. And that if you simulate all of these details here, then you can also look at how the limitation in nutrients and water is impacting crop growth, right? So some crops may quickly die during that process if you're looking at all of those details. But in CLM, because we're not looking at all those details, there's planting and then, the crop grows, you have crop yield and so on. Why this matters? Now, a lot of people talk about crop growth, crop yield, food production under climate change, high temperatures. And if you don't account for anything, then probably CLM gives you very good crop yield even at very high temperatures and very low water. So that's why we did this. And if any of you is interested, you can look at this. There is a temperature sensitivity simulated by the two models. And we clearly see when we have APSIM, it nicely captures the temperature sensitivity. When there's higher temperature, crops stressed out, and if there's no water, they can die. But CLM doesn't really capture that sensitivity. And even before going there, we validated this model, and there are a number of things we can do with crop model, like leaf area index, it is simulated, and then above ground biomass, and then this is the vegetation height and harvest index, basically how much harvest you get out of a certain amount of crop biomass. And look at this one, the circles are observations, and then this solid line is the new model, APSIM, and dashed line is the original CLM. Leaf area index, better captured here, but if you go above ground biomass, there's a strong indicator of how much crop yield you're going to get. If there's more biomass, it's going to yield more crop, because it's going to give you more yield, right? So here, this is nicely capturing, the new model nicely capturing this above ground biomass compared to CLM. So these are the things we can do by going into some of these details in the model. And there's more to that. I think I skipped some of the results, but I already mentioned the most important part is sensitivity to nutrient and water stress under a higher temperature. So this new model very nicely captures that stress, and we have been working on future simulations to see impact on crop yield and so on. But there are also studies published with just schemes like CLM here, not the one with APSIM. There are a lot of future projection studies as well, so it will be interesting to see, what kinds of, or what are the differences in results when we have better crop scheme in large-scale models versus the simplified. Okay.
Actually, one quick question. So here, this CLM AppSync,
Yes.
so has been applied global or like field size?
Oh, that's a very good question. And it was applied across the U.S., central U.S. at that time when it was developed,
Yes.
with all the Fox Tower sites validated, and I forgot how many, but now it is, it was already tested globally, even though there's no publication, and now it's an official CLM also.
It's an official
Yeah,
CLM.
yeah. Maybe it's not in the one that is already released, but being implemented.
Yeah. Yeah,
Vincent is working on that. Yeah.
So say if you're hitting a global CLM simulations, usually maybe at 1 degree or maybe higher at 0.5 degree.
Yes.
So at this kind of spatial scale, they incorporate those crop phenology.
Yes, yes, still works.
Detail.
Yes,
Detail.
still works. We need
Okay.
some parameters, but
Okay.
we can simulate those phenology because this was done at point scale to validate, but
Okay.
at the grid scale also we can do.
Okay.
And I was going to say something. Yeah, half degree is fine. I was going to say something. Yeah, but basically it's possible.
Okay.
Yeah.
I see. Okay.
Yeah, I was going to say something important. And then that is the crop scheme implemented in the model, and I will gradually move on to now we have crops, but if we do crops better, then we need to do irrigation better as well because a lot of these crops are irrigated. And how can we do that? How can we do irrigation better? As I said, I didn't explain how irrigation was done in the global simulation that I mentioned earlier. Anybody knows that here? That's the cause of it. How irrigation is simulated in these kinds of models, CLM? Maybe not.
Maybe not.
Maybe not. Okay. Then very simply in these large scale models, why I brought this issue up is at the field scale. In reality, these are farmers irrigating crops. So they use this in their intuition or use weather forecast to see whether there's going to be rain in the coming days or not. And different countries, different locations have different irrigation systems. For example, sprinkler system. In the central US, heavily irrigated area, how they do is central pivot irrigation. Maybe you haven't heard of that. Central pivot is there's something that goes around. It has a huge diameter. I forgot the diameter, but maybe 800 meter by 800 meter field, and that thing goes around and irrigates, okay? So for that to go 360 degrees, it takes 3 days. That's the central pivot system. Now farmers have to decide, is there going to rain in the coming 3 days? Then stop the central pivot because it takes 3 days to do this, and from tomorrow it's going to be pouring rain, so they just stop it, okay? And then they go and measure, soil moisture levels with probes they have installed in the field, and they see, oh, there's enough soil moisture, we're not going to irrigate. But here in the model that I explained, it's very simple. What we do is, there's this soil column, let's say this is the bottom, and then this is soil, okay? The model at every time step gives you, some soil moisture content. Let's say volumetric soil moisture content of 0.3, but for a crop, let's say wheat, we want to maintain soil moisture at 0.4. Volumetric soil moisture of 0.4, 0.5, whatever. I'm just making these numbers up. Then we want to have this volumetric soil moisture at 40%. There is only 30%. So the model calculates the difference. And we set the target. We provide that data into the model. Try to irrigate at this level for this vector or this location. Okay? There's a level that is always specified, and soil moisture simulated by the model keeps changing, and the target is here, actual is here. The model tries to bring the soil moisture up to the target level. That's how we do the irrigation in a very simple model. But in reality, this one shows this very nicely. There's a bunch of stuff here. See, this is irrigation. Which one is that? I forgot. Maybe this one. This one is irrigation. And then this is irrigation rate. So they, no, the irrigation, this is very old, 2010 paper. I didn't check recently. Anyway, there's model, basically what they have here is there's actual rainfall precipitation at regular interval whenever there's raining. This one model precipitation, and then there's irrigation rate, at what rate they do irrigation, and then the actual, I think soil moisture right here, soil moisture, right? So there's, what is the soil moisture level? So they track all of these things. How much is the soil moisture? What will be the precipitation? And then decide how to do the irrigation. So we cannot capture all of these things. What I'm saying is we cannot capture all of these things, and that's why we do a very simple approach. Most of the models, Earth system models, if you have irrigation, do something like this. set the target, and try to bring the soil moisture up at every time step or every day. And in CLM, it is irrigated every day at 6 a.m. in the morning. So you can change this also, but 6 a.m. model checks whether there is enough soil moisture. If not, then dumps water, bring the soil moisture up. Let crops use the water throughout the day. Next morning, again, check it, and then bring it up. So that is how it is done. And what we thought is, okay, so this approach may not be very realistic. So we decided to, kind of take this in the model, and for that we use map satellite data, because for using field data, there are limited number of locations where we can get soil moisture data that we can put into the model. And what we did in this one is we took the soil moisture data, top layer soil moisture data from SMAP, and then check or assimilate that into the model. At every time step, check whether the simulated soil moisture is consistent with this SMAP observed soil moisture or not, because SMAP is the real data, and we're talking about historical simulation. And by doing that, we were able to change the target. The red line here is original CLM target. It always targets at the same level, regardless of what's happening in reality. Okay, always same target, trying to bring the soil moisture up. But by using actual soil moisture data, we change the target irrigation threshold over here, which dynamically changes over time. Now what happens is the green line is much lower than the red line, red dots there, meaning that we are not trying to irrigate so much. The target is lower because there's enough soil moisture in the field at that location. So by doing that, we were able to significantly improve the irrigation simulation. And my point here is, the models have a lot of deficiencies. There's irrigation, but very simple scheme is there. And if you look at the central US, I'll jump from the left to the right here. This is difference in irrigation water withdrawal, model minus the observed or reported data. So if you see blue, the model heavily overestimates irrigation. It is irrigating a lot. If you see red, then it's irrigating way too less. If you just look at this aquifer height aquifer right here, by changing the target level for irrigation, we substantially reduce the bias, right? So the dark areas become way lighter here. And this one is called SMAP, and simple Kalman filter assimilation and bias corrected with some observational data. So this is one way to kind of capture the real world practices of irrigation. It's not really going to something like this. We don't know how they are doing irrigation and stuff like that, but at least by using some existing data, we can modify some parameters in the model, and that can help us better capture irrigation. Any questions? And I think I used a lot of time. I wanted to go very slow, but what I will do is I will talk about groundwater and a little bit skip to flood settlement, because I have a lot of slides I think, but just here on the second.
So for this one, so basically, if we have like observed data,
Yes.
then you can try to
retune the model, change the threshold, and in fact, it is assimilation. So if you have data, time series data, then at every time step, the model tries to kind of capture the actual withdrawal. The problem is, what do we do for the future? So, but this is one way to capture what's happening in the real world. And in the future, then the question is also, we cannot use this, but we also don't know how they're going to manage irrigation, right?
Sure, you can go to the plot.
Okay, yeah. Shall I move to the plot now?
Yeah, sure.
Okay. I have a bunch of slides here, guys, but I will. Oh, nutrient. Let me talk about nutrient stuff a little bit part of what we did. So for the nutrient part, we are doing this in the U.S. again, and this is Mississippi River Basin. I wanted to show this one a little bit. On the left side, there's heavily irrigated groundwater depleted system. On the right side, it's called corn belt. They produce a lot of corn, and again, they export. They put ethanol and gasoline in the U.S. from corn and everything. So the eastern part of the Mississippi is kind of the region where there's alarming rate of nutrient leaching. They put huge amount of nutrient, because in the past 40 years, they have increased crop yield by 2 times, 3 times maybe, by using the same land. How? By intensifying agricultural systems. And one form of intensification is adding, chemical fertilizer, specifically nitrogen, phosphorus, and nitrogen and phosphorus, right? So by doing that, they are intensifying cropping systems, but the consequence is all of that leads, and not all, but a lot of that nutrient or nitrogen leads us to Mississippi River, it goes to the Gulf of Mexico, and there's a big, dead zone. All the nutrients going into ocean, and nothing can survive in this area. So there's a big issue. People are trying to simulate. There are some studies, but still it remains puzzle. How can we, accurately estimate the nutrient flow and what happens in the future and so on. So in this study, what we did is CLM, the model for every grid cell, it gives you, if you look at this one, there is atmospheric deposition in CLM. There is input that goes to the land, that is nitrogen. And also there's mineral nitrogen. Farmers add, chemical fertilizer, nitrogen into the cropland. So you get all of those, and then there will be some sort of, nitrification, denitrification. Crops will take part of it, and so on. And part of that unused part leaches into surface water and groundwater. Okay, but in CLM, that's what happens. After bleaching, it doesn't go anywhere in the model. Each grid cell gives you some leaching, but then, what happens to that nitrogen? Where does it go? It's not done. So what we did here is we used a scheme that utilizes that Beckson dispersion reaction equation, basically nutrient flow and reaction in water. You put nitrogen in water and let it flow. What happens? How is it transported? How does it react on the way? How does it change its form, and so on? So we used this and then simulated, nitrogen transport across the Great Lakes. I'm from Michigan. This is Michigan, state of Michigan. I'm around here, so we wanted to see what's going on in the Great Lakes region. Partly because there are a lot of issues in the Great Lakes. This is Lake Superior, largest freshwater lake in the world, right? All of these lakes are heavily polluted. Again, I showed the Mississippi case, same here. So in this case, we are putting all the nitrogen leads into river. This is upper Mississippi here and all other river systems. And the color here shows tons of nitrogen, nitrate, NO3. There are different forms of nitrogen. This is nitrate. And tons of nitrogen or nitrate in each river location right here. And then we looked at how the model is doing. This is just one example that was looking promising or good. Green is model simulated nitrate load over here, and then the black dots are observed nitrate loads. So model kind of shows promising performance. And our goal is each of these lakes, how much nitrogen is ending up in each of these lakes. So this is Superior, Michigan, Huron, Erie, and Ontario in 5 lakes. This is the amount of nitrogen that flows every year. Okay, so this is an ongoing study. We are still working on it, but I wanted to quickly mention because something like this doesn't exist in many of these models. So we are still working on this. All right, any questions or maybe 10 minutes or so? Maybe?
Yeah, so maybe
When
we can discuss it.
do we finish? Already time.
5.
Okay, for 5. Okay, yeah. And then we can have some discussion. The other part is kind of flood modeling that we are working on, and on this one, maybe I can. Basically, many of these models do the river routing. Runoff comes from the model, and then it is routed through river channels, right? But the kind of flood model that we are using is a hydrodynamic model that not only routes the river, the runoff, but also does flooding, floodplains, water going to floodplains, and backwater flow, all kinds of things. And in our version of the model, what we have done is we have also implemented reservoirs, the ones that I mentioned earlier, because they have big impact on the hydrological cycle. So, and if you have a grid cell, if you have a model like this with finer grid cells, these are all grid cells in the model. Forget about this one for now. And then there's a reservoir over here. Within the reservoir also there has to be some exchange of water because that reservoir occupies multiple grid cells, right? So there's exchange of water between grid cells as well. And then there's outlet. The dam is right here. There will be outflow. So what we are doing is we are using some optimization schemes to simulate the flow and then determine what is the inundation in the upstream and what is the release in the downstream. So we call a coupled river reservoir floodplain routing system. We call Pima flood dam. And what the model gives or does is it takes the information on reservoirs. This was initially done for the US. There's a dam over here, and the model first of all creates how the upstream is inundated. This is the area, and if you look at the Google map, so it nicely matches. We had to do a lot of manual correction because if you wrongly put the reservoir in the wrong grid cell, then entirely different area can be inundated. So there was a lot of work done, but then finally you can represent this reservoir there and simulate the river storage, reservoir storage, and floodplain storage for large regions. And here this is satellite-based data for inundation, and then here you see the model. It's very difficult to validate the depth of water because the model gives the depth of water, as you see here. This color are over here meters, and this is a Colorado River Lake Mead. You see very deep water, like 100 meters in the reservoir. We cannot really validate, but at least from remote sensing comparison, we can see the patterns are very good. And I also put a third panel over here. So we are doing this at, right now even 90 meters after downscaling, but typically at 5 kilometers. If you compare to large-scale global models that have grids of 50 kilometers or so, then you see way different results. So my point was, if you really need to do or want to do reservoir floodplain simulations, then these global models can provide you some river flow, but not flood and reservoir. Okay? So you see this thing here, reservoir, very deep water, this pattern, but this is the global model for the grid cell showing a little bit of water over there, but all the patterns are gone again. So this is what we're doing. And the usefulness of this is we are also working with water agencies to produce water levels and storage in reservoirs, how they are changing, and can we use this kind of information for water management during droughts and so on. Right here, these are some of the locations where we did comparisons, and Lake Mead, black line is observation, red is model simulation, so we can nicely capture the water levels and storages in these reservoirs. Okay, and then the model was after validating in the U.S. because we have a lot of data over there. The model was used in the Mekong River Basin. I will skip this one because this is the model structure. You'll get runoff from a model, land surface model like CLM, and then you get reservoir information there, and this is the camouflage model with dams, all of that goes into it, and then the model simulates river floodplains and reservoirs, okay? And then this was applied in the Mekong River Basin. What we can do is, first of all, we were able to simulate the flood patterns. This is one of the lakes in the river basin over there. You can nicely see the flood patterns, the flood occurrence, at what interval the flood is happening, or how many days in a year flood is happening here. If you see dark color, then it's a permanently flooded area. Lighter colors, 40% time of a year flooded areas. Okay, so we can nicely do flood simulations. And because we also have dams in the model, we do simulations with dam and then without dam. First, do simulations by putting all the dams, and then remove all the dams just in natural simulation. If you do with dams minus without dams, we can see how dams are changing floods, right? And this is a different story, but here I would like to talk in a way that, let's say we want to see how flood will be reduced because of dams, if there's a flood control dam. Then here you see, by having a dam, you see reduction in flood. In this location, that's not a really good thing, but you see, significant reduction. This is simulation with dams minus without dams. So whatever you see red color, that means there's going to be way less flooding when you have dams in the system, and in this case, dams in the model. Whereas if you didn't have dams, like in the 1980s, the upper left panel, the colors are relatively milder, so you don't see much impact here. But here in Estados, there are way more dams, so you see bigger impact. And in the end, the point is, by having these dams in the model, you can, simulate the downstream impact. It could be impact on ecosystems, ecology, and so on, or impact on, or kind of change in flood in terms of flood protection, or whether there is flood risk. Okay? And maybe this is the same story. I will just take 1 or 2 minutes. In the Amazon basin, we are applying to the same model where there are a lot of dams being built, and see these are many of the reservoirs. The model gives you there's a dam over here, and right side is remote sensing. This is one dam, another dam, and so on. So right side is remote sensing data. Left one is the simulated. There's a dam over here. We put it in the model and simulate how upstream inundation happens. So you see it very nicely for a lot of these dams. The patterns are nicely simulated by the model. And the usefulness is if there are new dams that are being planned, or there are new dams that have to be that are planned to be constructed, like in the Amazon, where will you see inundation? What communities will maybe potentially displaced? So that's what we're trying to do here, and the model kind of allows us to see the potentially flooded areas in the upstream of dams. And let me skip that and thank my students and group members who gave all the results to me. Everything that I saw, except for the decade-old stuff in the beginning, is that was done by me. Others, all of the other stuff is done by the students, and there are 2 researchers and a few PhD students, 5 PhD students, and a couple of masters and undergraduate students, and also there are previous members who have recently left the group, but the Mekong stuff was done by Sang-hyun, CLM was done by Farsid, we did Amazon, and so on. So these are people who contributed, and I always thank Fulbright, as Professor Lowe said. I'm here through the Fulbright program, and finally, everything we do is funded by NASA, National Science Foundation in the US, and so on. Thank you so much. I think I took my time for that.
Thanks very much for giving us like a pretty comprehensive this modeling work that you have done in the past more than 10 years. So from global model and then go to regional perspective that actually can be used to simulate regional or local. So I think maybe your next step you try to simulate Taiwan's river runoff.
Yeah, that one I didn't add today because I thought I wouldn't have enough time. So we are applying the FEMA flood model for Taiwan. We already have some results, but I didn't put them today.
So that's quite flexible modeling framework.
Right. Yes.
Okay. Any questions?
Yes.
Fantastic works. You did a lot of job to downscaling the CLM model to and also increase the numerous components in the motion and the code. So I just have one question is that when you're talking about the nutrient flow,
Right.
you use the relation and diffusion
Yes.
equation.
Yes.
To simulate the nutrient change, right? Just wondering how to deal with the term of source and sink.
Oh, in the equation there is
Because in my opinion, I think that term probably is highly associated with the core,
right.
the core growing or
Right, yes. Yeah, I think there's sink term, source and sink term right here, over
Yes.
here. This one.
Yes.
This is the reaction term, there's reaction coefficient, and then there's a source and sink term over here. So that takes into account source of nitrogen and also how it is, taken away during the process. So we take into account, and that depends on all the crop processes and how the crop utilize the nutrients and so on.
Yes, that's also what I think.
Yeah.
And the second thing is that if you can model the outflow of the reservoir,
Right.
the building reservoir, before reservoir or after reservoir,
After
I just wondering, can you estimate the residence time of for each dam or each river? Because the residence time,
residence time.
yeah, with older.
Oh,
Numerous,
yes.
for example, energy, for example, so
Yeah, I think we could do, we haven't really looked at the residence time, but that is entirely possible. There are so many things we could do, and when we develop the model, we always try to look at the first order thing, like how can we better reduce flows and so on. But yeah, I think that's an important point. We'll look at that.
So is the residence time for the dam or for the
For the
whole
river.
system? For the whole system, for the river.
For the rivers, yeah, when there's a yeah.
Well, there are many papers discussing the residence time regime of river.
Right, right.
With the order water cycle and which cycle.
Yeah.
Yes.
So if we can evaluate the effect of the dam,
Right. I think this is very important. Charles Forrest Marty at New York University published a paper in 1997, like 45 years ago, on residence time of reservoirs or something like that, based on some observations. And a lot of modeling done, but none of the modeling groups are really looking into that aspect. So I think it's an important point here.
and it seems to me that you also have some regional models.
Yes, we apply it at the regional scale. Yes.
For example, the last part of it is when you're talking about the flood, you have the regional model and also have the CLN, and you want to couple it or
Yes, another good point. Yeah, this is the model that we applied at the regional scale, and right now we are running CLM at the same for the same river basin, Mekong, at the regional scale. And CLM runs at 5 kilometer, and this one also runs at 5 kilometer grids. We downscale to 90 meter for the flood, but they run basically at a little coarser resolution. So we are coupling these two. So over the Mekong and also in the southwest US. We are fully coupling these two models. Yeah.
okay.
Yeah, those are really, really good point and kind of what we could do further.
Maybe we can have a deep discussion the next Wednesday.
Yes. Yeah.
Looking forward to see the result of Taiwan.
Oh, yes, we can still take a look at that also. Yeah, today I was thinking whether I put or not, but maybe we could.
It's okay.
It's okay, yes, yeah. Something for next Tuesday, something new. Next Wednesday.
Any other questions?
Yeah, anything basic question is fine, or on the results, or anything. Please don't hesitate.
有任何问题来都可以问。没有。Anyone? Yeah. Give it a try. 来吧。来吧。
Then call for next time.
So maybe I add one more that based on Professor Yuhong's first question about
Right.
nutrients.
Yeah.
So that means we need to know how much the farmer put the fertilizer.
Yes.
Or-
Yeah. Yeah. That is fertilizer input from U.S. Department of Agriculture. USDA gives
so for
county-
US.
USDA gives county scale fertilizer input for each county.
Yes.
And then we, based on where irrigated areas or crop areas are within the county,
Yes.
we make a gridded areas. Because we exclude cities and so on and just equally put that amount of nutrient.
Within that.
So we have the model needs per square meter of crop area, how many kilograms of nitrogen they put every season.
I see.
So we put that as input. And the other is the atmospheric nitrogen deposition that comes from input already. Just the nitrogen deposition, natural. So that's in crop areas it's relatively small because the artificial chemical fertilizer is too much.
But the nitrogen deposition in Taiwan is quite high.
Quite high.
Yeah. It's around 2,000 kilogram square kilometer.
Oh, really?
Yeah. Because most of them are come from mainland China.
Mainland China, right? Yeah. That's interesting.
It's quite different from Taiwan and USA. USA is only around 500 kilometers.
Something like that. It's too small.
It's pretty small.
Pretty small. When they
200 to 500.
right. It's pretty small when they compare to the chemical fertilizer. So it
So
doesn't
don't
make.
worry, Taiwan also has the fertilizer application data.
They are available.
Yeah. But the question tends to be how the nitrogen process, for example, from nitrogen ammonia or ammonia to nitrogen.
Exactly.
That's the key.
Yes.
Is Is that within the EU regulation?
No, there's not in the
Only use the nitrate because nitrate is the most stable nitrogen.
stable nitrogen and most dominant form of nitrogen. So they focus on nitrate. They focus on nitrate, and we haven't done phosphorus yet. There's another one. Different forms of nitrogen, and then also phosphorus.
Phosphorus.
Yeah.
Nitrate should be the first because, as you said, the Mexico
The Gulf of Mexico. Yeah, very serious issue. They have made a lot of investments, but still a lot of uncertainty, and people get every year people get millions of dollars in trying to study this.
Crocodile is mainly from nitrogen fertilizer.
From the nitrogen.
Yeah, it's a really big issue there. And the size right now is close to the state of Massachusetts. This dead one. Yeah. It's pretty big.
Okay.
Yeah.
Thank you. Okay, if there are no.
Yeah, feel free. Also later on, if you have anything, I'm happy to talk, or if you'd like to send me an email or anything, that's fine too. And also, I think I should have had a slide about whatever I do a presentation and whether our students, if anybody is interested in doing further study in the US, also contact me. There can be opportunities. So I did put that slide. I should have probably because
Next time.
I didn't make the presentation always with students, so sometimes I forget to do it. So yeah, please feel free to contact me if you're interested in graduate studies in the US. There can be opportunities, or I can provide some information.
That's good.
So yeah.
All right. Okay. Let's thank Professor Yadu Pogara again. And as I mentioned, he will be here for another 2 months.
2 months.
Yeah. So please talk to him.我再给你。好。看看看。
帮我。
我看。因为他那个出来的啦，他们那个。
They created a Chinese name for me. Yes. Still ongoing studies. Yeah, we have not published yet. Yes. Yeah, still working on it. Thank you so much for coming.
好，那我们今天就到这里为止。有没有任何问题？那因为亚度 use COM， 所以你们企业在用 COM。那当然有一些改的，我想有一组要讨论 irrigation。You can turn on, turn off, and let us know what's the impact from that irrigation over there. And the dams, as Yadu mentioned, the reservoirs is not in the COM at all, but it's actually is in his Japanese model already, right? So the concept should be adaptable, portable
Yeah,
to COM.
recently somebody put it in CLM.
Already? Okay.
On Museum, but the results were, they put a simple scheme, and the results are, there are a lot of issues because we couldn't really, I'm a part of that also, but couldn't really produce something like I sold.
So it's in COM or in the
In COM.
here?
Oh,
Should be
it's
in the-
Miserable.
In Mizo, in the Rocky model.
So, yeah, and maybe some of the stuff, I deliberately talked about what are the limitation kinds of things, because maybe you guys can think about, where things stand in terms of reservoirs or irrigation or dam in the current model, and what are the possibilities, opportunities. So, yeah.
好，有任何问题可以再寄 email 给亚度，如果你们需要的话可以跟我讲。好，那我们今天就先到这里。好，谢谢。
Thank you so much. Thank you for the